Morning. It's July 9th, 2017. Doug Littrell again. I've got a few more things to explain with these pitfall type experiments. I made another video that I haven't combined. I'm going to combine it with this one yet. I haven't combined it yet. I'm going to combine it with this one. First of all, I want to say with the wand that I've been using, that I've now made the end of it black so the tiny aluminum bead would show up against it. When you rub this, remember that I showed in one of these videos, I'm going to try to speak up because I know I'm far away from the camera. Anyway, when you rub this, rub one end, what I showed is that this end gets disturbed, and you know, the effect. I'm going to pull this over. Here's that hollow plastic ball. Let's see, let's move it back like that. Okay. And it's attracted. Okay, the other end, almost not at all. Look at that. See, what that tells you is that it's the effect of loading up with electric photons is bleeding. It doesn't just spread immediately. This is a insulator, so you know, it's PVC, it's plastic, and it doesn't let that spread. This confirms, this is going to confirm or help reinforce in a strong way what my interpretation I gave yesterday for why the rubber and plastic and wood objects, there's the surfaces are disturbed, but then some of the photons are bleeding further deeper into the material. And that confirms it. Now, we'll see. Is it attract now? Now, with this, I've got a styrofoam bead here. Sometimes it just, you make wind, and it'll blow that. But it still hasn't hardly, it's still a little bit attracted to this end. So that tells you that what I said yesterday with these insulators is correct, that it bleeds gradually. The change of the electric photons come in. I mean, that explanation holds up, appears to be verified. On the other end, well, let's get the thread over a ways. I was doing something with this bead, this styrofoam bead that didn't have any aluminum on it. I was doing something with that a couple of days ago, and I'll probably be adding that video to this one. But look, there's almost no attraction on the other end. Look at that. Okay, so that another thing is just the thickness of the material. And that's why the hollow bead, or the hollow ball, plastic ball, works better than that rubber ball that's solid. And here you have a thick wall. This is 1 inch PVC. They're both 1 inch. But this is thick wall. The other one is thin. Now, just because there's more mass there means it's going to have to bleed from the surface where it's being disturbed into the interior, and that's why the heavier, the thicker wand isn't as good. Now it's working now, but I rubbed it an awful lot. When you compare them, uh, the thinner wall with the, see, the thinner wall can't, it doesn't have to share it across an expanse of material. See, it's sharing, and now it's almost not attracted at all already. We're bouncing it. Yeah, it's dissipated already. Now let's rub this one. About the same amount that I rubbed the other one very aggressively. Oh boy, look at that styrofoam bead come over. Okay. And what you're going to see is that this lasts a lot longer because it's not bleeding off into the thicker material, the thicker pipe. You can't take these things for granted, you know. You have to investigate them thoroughly. It's just like the equivalence principle. You can't throw a couple of rocks, drop a couple of rocks off of a big rock and little rock off a tower and then make a accurate conclusion from that about how things fall through space with different masses. You can't do that. You have to check things thoroughly. Look at that, it's holding on. And I've done this before, and it will stay attached for, well, with 20 rubs, not as aggressively as I rubbed it this time. It stayed attached for some, and pulled over about 4 inches for about, it was like 13 minutes. So you can see that this is much more than the heavier material that has more material for the effective bleed off into the interior. See, that proves that there's, for me, that helps prove that there is no such thing as negative charge, and that my explanation I'm giving on these videos is correct. Now here's the heavier one. I probably held that other one over there, what, maybe 3 or 4 minutes. I didn't time it. Now it would also help if this one were longer. It would have more material yet for it to bleed off. I rubbed it pretty aggressively, so it's, you know, I gave it every chance to beat the other one. It's already dissipated. It won't pull the plastic, hollow plastic ball over anymore. Now let's look at this, or very little. This is the one I haven't rubbed it, and look, it's still more. It's still holding it, you know, what, some 2 inches away? Look at that. That's the difference in thin wall and thick wall. See? That's not bleeding off into the atmosphere. It needs thicker, heavier material, interior material for it to share, for those nearly filled but not filled radio shells to share electric photons with, and for that to be bleeding off, and so the traction remains as long as they're being fed in the attraction remains. It's what the attraction means. When there's repel, there's no, of course, the conductor, the tiny bead down here. I haven't even rubbed this. It's attaching because it's loading up again. It's loading up, and if I had this rubbed enough, it would not just fall away. Now it's repelled. See? Now it's repelled. Can you see that? That bead. See, there's a conductor. That's the difference right there. When you know what's going on with this, you can just repeat it over and over and over every time. One thing, you know, I could make a very small, well, that's what I did with this styrofoam bead, was I was trying to get it to act like a conductor. I could not get it to repel, you know, how the conductor attracts, and then it suddenly starts to repel. Well, you can't get the one without the aluminum on there. I think I got that in another video I'm going to share. You cannot get it, the styrofoam bead, to do that without the conductor on the surface. So I'll include that with this. I want to show you what I'm doing. I've already started my new periodic table. I'm going to show you that. I'm going to show you now the new periodic table that I'm working up that doesn't rely on negative charge in its explanation. And it has these radio shells out to each noble gas, and that explains why some atoms why some elements are noble gases, noble gases. They make noble gases because they're radio shells. They all have a certain type of radio shell. The ones below them in the chart have a lesser filled shell. And then when the shell is filled, then it's a noble gas, and that would have, like I said yesterday, that would have the lowest number of nucleons with the greatest protection of a radio shell, keeping other atoms away from attaching to it. That's why it's a noble gas. You can almost look at the periodic table and see my atom model. It's just there. It's just right there. You've got, now I misspoke yesterday when I said there were two radio shells. I'm just getting organized with this. So, you know, once, you know, I've got it together, then it's going to be easy to remember everything, you know, but it's still, you know, I'm still like moving pieces around, trying to get all the puzzle pieces to fit perfect, you know, at this stage. But anyway, the R3 shell goes from protium to helium-4, and helium-4 is a filled shell. And then lithium up to neon is the next shell out, and it's the R15 shell. The first shell is the R3 shell. The second shell is the R15 shell. And so they're lithium and 7 and 6 more, which makes a total of 7 between helium-4 and neon. And then neon is a filled radio shell of R15. You know, all of them from lithium or from helium-4 on up have filled R3 shells, but over that they have partially filled R15 shells. And then, of course, after neon, then the next shell out is an R4 shell. And then, so sodium would have the least filled shell. Then magnesium has a little bit more filled R4 shell. And then you get to chlorine is the number 7th after neon. And then number 8 is argon, the next noble gas, and argon has a filled R4 shell. And now the nucleus gets bigger and progressively bigger, and then when you add nucleons, you know, whether it's a couple of protons and a neutron or whatever the next step up in the elements are, you know, you're not adding as significant a percent of the nucleus like you are when the nuclei are small, and especially between helium and lithium. You know, you go from helium-4 to the next stable atom up element is lithium-7. You go from 4 to 7. That's a tremendous jump in mass. You don't have that when you get past argon, and that's why there's 17. You're still adding, you know, radio particles per the number of photons. Now, here's another thing I need to mention. What I figured out, you see, helium, when I looked at what I had done so far using 80 or 88 radio particles per proton contained in a nucleus, and say 100 or 110, say, radio particles per neutron, I went back and looked, and it wasn't very far off with that. I just needed to add more per each proton and per each neutron. And so what I didn't mention yesterday, which I had already found out, was that what needs to happen is that when you're doing this, you need to add 100 100 radio particles per proton and 125 per neutron. That makes it come out right. Now it's probably not going to be perfect, and it might be refined down the road, but that's good enough to get started with this. It should come out just right, I believe. It's already come out perfect with. I've gone to helium now with the R3 shell, and now next is going to be the R15 shell. And if that's the right number, then it's going to come out where neon is going to be filled with using those numbers. So we'll see. But I want to show. I want to show what I'm doing. I've just started this. This is in. Now I need to get a new phone because the camera, only one of my cameras on my phone works. I have to hold the phone, the screen facing the whatever I'm filming or, you know, recording. And hopefully you can see. I have to look at it. I don't know. But anyway, so there it is. It's in, this is in the free software, paint.net. And I've used that for basically all of my drawings that I've been doing for a number of years. But if you can see that, you've got the first element is protium. And right now, you know, they consider deuterium to be another version of protium because they think that a proton has a positive charge and that electrons have negative charge. But that's an erroneous interpretation. That's why I'm doing this periodic table this way. Deuterium in my system would be essentially another element, and then helium-3 after that would be, it behaves like helium-4, but in my system you would treat it like its own element. And then you have tritium after that. You treat it as an individual unit separate from any of the others as well. It definitely behaves different than the others by far. And helium-4 is next, where you have the first filled R3 shell, and then lithium after that. Lithium was where the beginning of the R15 shells come in, and there's a scant R15 shell over lithium-7, and that's what it's showing. There's no way to show that it's that like the one over deuterium is partially filled or over helium-3 is partially filled. and over tritium is partially filled, and then over helium-4 it is completely filled. I'm just going to have to notate that on the chart. Another thing, now, well, let me mention this first. Protium, well, I need to explain first that there's a difference between model pixels and chart pixels. I can't use the model pixels, which have the photon, the smallest digit in the universe, being 13 pixels of diameter. Because if I do that, and if I use that, the chart would be too large. So I have to use these nucleons. The proton is 24 pixels of diameter, and the neutron is 25. Now, in reality, they're not going to vary by that large a percent, but still, the neutron is a little larger. And so that's what I'm going to use to represent it, 24 compared to 25 pixels of diameter. Now, I've already done this. It's in the book with protium, deuterium, and I've got my distances from the nucleus already determined. Now, I had an electric layer, which I've deleted now. That doesn't make any sense to even mention it because it wouldn't have anything to do with electric transmission that I can, and there's going to be, look, if there were electric photons next to the nucleus and some of them got scattered off, those would immediately attach because they're right there. You wouldn't need for a magnet particles to come in from the environment. So there is no such thing as an electric layer next to a nucleus like I was drawing. I did that because the single photons are more fleet and they always beat anything to any spot. I thought there might be a layer there and it might have something to do with electric current, but I had to abandon that. So it doesn't exist. It's not there. But my distances of my shells from the nucleus are much closer than the standard model. And so I'm going to go ahead and leave the distances that I determined using the very thin electric photon layer that I did. I'm just going to keep those because there's probably good reason to have, not to shrink these any more than they already are, relative to what's thought about the standard model, with its very expansive electron shells from its nuclei. But I believe this is true. One thing that helps solve that is the repel of these particles, these photons, as they fly through the environment. Their repel helps them plow through and not have collisions. There's still attrition, but that's one thing that wasn't realized about light, is that a lot of these particles in visible light, particularly the leaders in white light, have repel, and that repel protects them from collisions. Okay, so using the same size of the R3 shell that I used in my book, and it's also on my website. It's larger on my website. The R3 shell, okay, let me say this next. The diameter being 25, let's say, of a neutron on this chart pixels. That in the model, the diameter of a nucleon is basically 192. Now, I may have gone to the extent of saying that the diameter of a proton in the model pixels is 192, and the diameter of a proton of a neutron is 194. But anyway, it's basically 192. And so what we're doing is we're converting 190 to get this small enough to be on a chart. We're converting this to from what is in the modeled pixels, what is 192 is 25 and 24 here. So with those pixels, now you have to do things proportionately. So I did that with the math I was using yesterday. And instead of like in my, if you're using the model pixels in the table like is in my book or on my website, you would have, like say in helium-4, you would have, I think it's 644 diameter, pixels of diameter for the R3 shell of helium-4. I think it's 644. I think down here, I think helium-3 is 624.7 or something like that. But when you convert those to chart pixels, now it's the R3 shell is 88 pixels of diameter. When these are 24 and 25, this becomes, instead of 192 and 194, say, this becomes 88 instead of 300, or excuse me, instead of 644. So anyway, this R3 shell has 88 pixels of diameter. This R3 shell has 84 pixels of diameter. This one has 81 pixels. This one, the deuterium, is more of an oval. It has it's 59 on its short side and 79 pixels on its long side, what I've come up with. And then on the in protium, it's just 49 pixels of diameter for the R3 shell in the protium. Lithium is when you begin to have the R15 shell, and so you have the, if you can see that, there's a light orange R3 shell, and that's its diameter. And it would be filled, of course, over lithium. They have to, because of the repel, where that shell locates and how large it is depends on the diameter of the nucleus, because it has to maintain distance from the nucleus. That's the way all of this is set up, is maintaining the proper distance from the nucleus. And then, so it would have a wispy R15 shell, and that's what the green overlay of that orange. You can still see the orange, but there's the green represents, oh boy. The green represents the R15 shell. And then you're going to have progressively more filled shells with beryllium, boron, and their stable forms. I'm going to pick one leading stable form of each one for this chart. You can't, you just have to do one. There will be other isotopes, of course. Some of those, as you get into larger nuclei, there's often 2 or 3 stable isotopes. I'm only going to show what I consider to be the leading isotope on the chart for each element. Anyway, so let's see, is there any, oh, yeah, I guess that's all I need to mention at this time. Yeah, and of course I'm going to notate on here that each, I'm going to notate the chart pixels compared to the model pixels. That'll be notated on here, and as well as the assigning 100 radio units per proton and 125 per neutron, and that's the way this is going to work. This time there's a bead that's attracted. I made a new bead. This time no styrofoam. I wanted it to be the analog of these plastic and rubber balls, wood. It's real light, real small, has low mass. Like you can see that it's attracted. It's not touching a woman right now, but it's moving with the wand. Now if I bring it toward me a little bit. Let's see. I can get it to attach. But what you're going to see with this is without the conductor, there's a big difference. You're never going to see repel out of something like this. It's plastic or wood or rubber used in this way. Okay, I've got the thread pretty much taut as you're going to get it. And it's not touching right now. It's just taut as you're going to get it. I'm going to try to get it to touch, so that if discharge was possible, like it is with the conductor, then you should have a build-up in it, and then it should leap away like the conductor did, But this is a static situation. Now it does dissipate. Now with the this hollow plastic ball that's painted with a metallic paint, it stayed connected to the wand 4 inches removed from where it would hang by gravity for an hour. I had one that, you can't see this one, but it's the rubber one that was painted with a metallic paint. That's not a conductor, however, at least not according to my own meter. I'll double check that. Okay, I've already checked this many times with both ohm meters, but let's do it for the sake of of the video. Okay, I've got it on ohms. This most sensitive setting, or let's just make the second most sensitive setting. It's on 1, which means there's no continuity. And okay, nothing, no reading at all. Yeah, the same for the other one. So, when I did this experiment with the 2 metallic painted, one was a rubber ball, one's a plastic ball, the hollow plastic ball stayed attached to the wand for an hour. The rubber one, when the rubber is not very attracted now without the metallic paint, but with that metallic paint, it stayed attached. Now I didn't pull it over very far because there's a lot of mass there. There's more mass than there is with the larger hollow plastic ball, but it would move it over about an inch was all it could do, but it stayed attached for 3.5 hours. So there wasn't any transmission occurring, it looks like. And I think the same can be said with this styrofoam bead. Now it's not. It was touching. Now it's not. But you're not going to see the styrofoam bead it's not going to jump away with repel. All it will do is the same thing that this hollow plastic ball did. It was attached for 13 minutes when I moved it 4 inches over with the attraction compared to the one with the metallic paint. So that's all you're going to see the same kind of situation with this. It's going to dissipate. It's going to lose its attraction, and that's it. See, there it's attracted. There it's attracted. It's attracted. It's attracted. It's attracted. But, you know, if it were a conductor setting on top of, you know, so the foil was on its surface, which made it a conductor, and it was that were setting at the right distance away. So it just would barely touch as it's attracted, you know, with the conductor, there's a transmission occurring, and then the transmission puts more repel into the conductor, and then it jumps away. And you're not going to see that happen with this styrofoam bead or any of these others, the wood, including the wood. Now I can do the wood as well, but I thought the styrofoam bead would serve as an example for all of these. That last segment that I added to video 32, where I was using the wand relative to a really small styrofoam bead that wasn't covered with a conductor. That was done before I came up with my explanation that I've given now in this video and gave in the previous video, number 31, where the mistake I made at that point was I hadn't yet understood that there is a transmission going on in the insulators of the what I call the electric photons and the conductors, but there is also a transmission in the insulators, but it's just moving very slowly, and that, you know, it's if the proper explanation is that you have you know, nearly filled, but they're not filled. They're not filled radio shells over the elements. Now, this would affect molecules too, because when molecules combine, there's a lot of covalence going on. But when you have shells that aren't filled, but they're kind of close to being filled, that looks like to me is what makes the best insulators. And so, and some elements would be like that. Sulfur looks like it's one of those to me. And so what they're doing is, and I've said this before, and I didn't say it correctly in the last segment of this video because I hadn't reached the explanation yet when I made that, but I wanted to show how the styrofoam bead behaved relative to the rubbed wand. But anyway, there's a disturbance on the radio shells that are not filled, but close, kind of close, and the electric photons come in and supplant some of those radio particles because they're more fleet and with less mass than the radio particles that are lost. They come in and take their places temporarily in that outer shell that's not filled and not too far below being filled. Anyway, what they do is when they're entering those outer shells on that surface of that material, that causes the attraction. And then why it continues to attract is because there's no covalence, and then because the shell is too filled to be covalent. It's not completely filled, but it's too filled for covalence to be a conductor. And so it feeds along in the shell over to the opposite side next to another atom with its outer radio shell, and it feeds into that. And it's gradual. It's gradual. And it keeps feeding. That's why the attraction continues. And everything is just too slow. It's just too slow. So that's the explanation. Okay, I want to include more about the new periodic table. It's based on there not being any negative charge not existing, and it's based on different concepts. You know, that all of the radio particles have mass and they form shells out from nuclei. I'm going to have to turn the phone around. Hopefully I can show what I need to show. Working on this new periodic table, I've added beryllium 9 now, but I want to talk about that a little bit. I've added the number of radio units per nucleon now. You know, there's 100 per proton, 125 per neutron for any given nucleus that would reside. You know, whatever shells they make, that's how many radio particles the nucleus demands. And there are 100 in protium. There's 100 per proton, so that's all there is to that. There are 225 in the R3 shell over deuterium, because there's 100 for the proton, 125 for the neutron. Helium-3, there are 325 because you got 200 for the 2 protons, 125 for the neutron. The 2 neutrons in tritium demand 250 radio particles over it. The 1 proton, 100, so you got 350. R3 units over helium-4, you have 450. R3 units over lithium-7. Now, you have to figure the, I've already done this in my previous table and what I have already drawn and written. When you're figuring, well, let me say this first, that you have to figure capacity, and the capacity for the helium-4 nucleus, its radio complement of radio particles, the capacity is 448. Now, this has exceeded it by 2, but I would say that if there are 2 of the next shell, which would be R15, out there, that it behaves as though they're not even there. They're so insignificant. And this probably isn't right on the money yet, but let's just go with it for now. But you have the filled helium-4 R3 shell, and so it would behave like a noble gas because of that filled shell. And the shell might be farther out than that, but as far as I can tell, these shells, there has to be good reason for the distances they occupy from a nucleus, and you can't just stick them out there anywhere. There has to be actual felt repel between these, according to the amounts that I've come up with, which all makes sense, and they're progressive, they're incremental in their amounts, which is in my particle system. It's in my book. But anyway, so how do you figure that helium-4 has a filled shell of R3, and then it probably doesn't have any more than just that one completely spherical filled shell? You take the nucleus diameter, then you establish the distance you think the repel would cause away from the nucleus for the R3 shell. Then you figure the surface of a surface area of a sphere. Okay, and so now you decide how much repel the R3 unit. It's only has a mass of 3, so it and you figure out how strong the repel is of the particles that repel on the surfaces, and then you come up with a number based on the size of the particle, the radio particle involved, and the amount of repel. And so that's how I figure the capacity for that R3 shell is by surface area and also by the amount of repel and the size of the unit. You do the same thing with the R15 shell. Now the R15 is a much more massive particle than an R3, and it has a lot more volume, occupies a lot more volume, so you can't have as many of those as the R3. Now the reason it's there so close in to the nucleus is because its repelling particles are a lot milder than the ones that are on the R3, but there's more of them. So anyway, you figure the size of the particle, you figure the amount of repel it would have relative to the spherical shell below it, and then you plot those out there at that distance, and you figure the surface area of a sphere. Then you figure how much distance between them, and anyway, you come up with an R3 shell has a capacity at this distance of 423, and then the R15 shell has a greater capacity. So whatever's left over, now there would be 750 needed radio particles for this complement of 5 protons and 2 neutrons. And so 750, when you fill the R3 shell to 423, now that's the capacity. Whatever's left over is 300 of 750 is 327. You put those in the R15. And if the capacity of the R15 shell at this distance allows for that many, then you're done. They're there, and it's not a filled shell, but they're there. Now, when you move into beryllium, I've added beryllium now too. When you move into beryllium, now it gets even more interesting, because this R3 shell is a little bit. It has a diameter of 92 compared to 85, so it can hold more. Its capacity, instead of 423, it's now I'm not writing capacity on here, but anyway, because that's filled, that capacity is 423. It's 484 in the beryllium 9 nucleus. So now there's 975 when you add all of these. That's how many radio particles there would be if you add up all these nucleons and what they would pull in. So the R15 takes what's left over from the 975, but the only thing is, since the R15, the capacity is less, and what you find out at that distance, it has a capacity of 375. So you fill it to that. Now you still have 116 left over, and they will go to the next. So I need to cut this off and redraw it and put an R4 shell, and then it's going to have 116 units in that. And that's the way this works. Now we'll see if it comes out so that neon makes sense as a noble gas. We'll see as time goes on, as I keep working on this.